Would you please make him very, very welcome, Professor Iver Cairns.
So it is a pleasure to be here. Many years ago, I sat in a similar place to you for mathematics at summer school, and was amazed at what was there, having not really considered that I was someone suitable to go to such a school. But I went there and found that actually things were not so different and that I could achieve at a level that I didn't expect. And similarly, as Chris said, I didn't ever expect to go into the world of actually building satellites and flying them into space. It turns out that I and my team are the first Australians to put an Australian-built CubeSat into space. Only the fourth Australian-built satellite ever to get into space as well and work. I guess I've now got two in space at the moment, both this size, a so-called 6-unit CubeSat, which I'll talk about in a moment. There's 4 total that we've put into space. Australia has a certain number that I'll ask a question about later on, and yet my path was entirely different. At high school, I expected to do chemical engineering, and I thought, well, you know, maybe chemistry itself. And then a family friend said, well, you know, engineers always get a job. Scientists perhaps don't, especially not in the current international setup. And so I thought I should do engineering and science, chemistry, and then in 3rd year I saw the light, so to speak, and decided to become a physicist. And even then I was a theoretician, like Chris said. I worked on theories for waves and radio emissions in space, nothing in terms of actually doing the experiments themselves, except that my PhD supervisor, Don Melrose, thought it would be a good idea for a theoretician to, with a scholarship perhaps, to go across the world and see some actual data before it was published. And those data, you know, didn't come in a nice little hard drive or something. They came with big magnetic tapes, you know, basically this size. A satellite would fill one of them every week, maybe 2 weeks. Now, of course, my satellites, for instance, if they were working at full capability, would take one single image would be 1 gigabyte. Huge, orders of magnitude different. So the world is totally different now from what I expected it to be. The same will be true for you, and you should be seizing the day and following things that you think might be interesting and not necessarily expecting to end up eventually where you think you will end up today, but instead follow your path. And it will be difficult at times, but it will be fulfilling as long as you're positive about it. So I'm going to talk about CubeSats. I'm going to talk about satellites in general. I'll lead into space weather a little bit, which will be my topic for tomorrow. And on the way, I'll talk a little bit about Harry Messel and Sputnik, so the first satellite to get into space, and a connection to the school. But I'll also connect to industry. Many of you perhaps want to go on into university and thought, well, there's a good chance I'll become an academic with a PhD, etc., etc. And that is a really good goal to have. But the truth is that over 80% of our students going into university don't go on and become academics. Instead, that's 2%, 3%, sort of number like that. Even our PhD students don't all go on to become academics. Most of us, or most of them, go into industry. I'm one of the few, perhaps, who's dabbled in industry at the moment as well as academia. So think about industry and the greater possibilities of going out into the world and changing it for the better. But for us now, we're going to talk about satellites, what they can do. Here's an image of the thousands of satellites that are in space at the moment. This is just low Earth orbit. My vehicle, anyway, is CubeSats. This is a 30 centimeter by 10 by 10 one, of which this is a scale model of CUAVA 1. And I'll talk a little bit about some of the things we can do with that sort of tool or device. So let's see. Do I have to point in a particular way? Perhaps be old-fashioned. So first of all, what's a satellite? It's basically just an object, whether it's natural or a machine that orbits another object. And we'll be talking about machines orbiting the Earth. Yes, I could talk about projects involving, for instance, the Voyager spacecraft, which is now beyond the solar system, that I have an active project on. But we're going to talk about satellites going around the Earth. And so this is the outline. I'll start off talking about Sputnik, Harry, and the University of Sydney, which I'll come back to right at the end. I didn't believe I did that. But anyway, whoops. Talk then about some of the CubeSats, and then we'll come full circle to Harry again. So Sputnik wasn't the official name, actually, of the Russian satellite, but it became that. Humanity's first satellite. It was 1957 that it was launched. It re-entered about 1 year later. This is an image of it here. Not very big, something like this size, but then with long radio antennas on it. That's the things that make it look a little bit like a War of the Worlds type alien here. And it had a radiation detector on it, as well as a little beacon that went beep, 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 that scared a lot of people because they didn't want the Soviets at that stage to have the capability to put something into orbit that they didn't. But there was a communications issue. They couldn't get the data back from it. And it turned out that our Harry Messel, who you've heard quite a lot about, he's infamous for all sorts of stories, and I won't go into any of the juicy ones. But one of them was that he and his friends or colleagues actually had some radio transmitters, and they knew that there was this satellite going up, and they thought, let's listen to it, and then let's actually take down the data from it. And they were all very happy because they wanted to then analyze those data. Turned out they were encrypted. The Soviets at that stage were not particularly trusting, and they wanted to be able to publish the data themselves for the first time. Perfectly reasonable. But they didn't have the data. So Harry suggested that they should collaborate. Personally, I think this was a reasonable thing to do. That offer was refused. So the data stayed at the University of Sydney for something like 25 years before they were ever looked at again. And during that time, Jim Van Allen, who I met at the University of Iowa as a young PhD student, put Explorer 1 into orbit and measured the radiation belts around the Earth, which are energetic particles bouncing back and forth between the north and south poles of Earth's magnetic field. And he was the one who then discovered it, but the data was there. And it could have been a University of Sydney / Soviet Union discovery. But I'm going to show some data from the CUAVA 2 satellite, and I'll show a little bit from Inspire 2 as well, which shows such radiation. So some questions. I've already told you the answer to the first one, but how many Australian-built satellites do you think have reached space? So numbers, let's say, any votes for 1? No votes for 1. What about 5? Okay. What about 10?
You're pressing on somehow.
Okay. This is one of the problems of trying to be a little bit too sophisticated. But at least I don't have the answers there. Okay. So what about 10? Okay. It's a good number. 20? Yeah, I actually don't know the exact number. I was going to look it up and work it out, but I think it's approximately 16. Of which 4 from my school, at least 4 from the University of New South Wales in Canberra, 1 from UNSW Sydney, 4 from Binar in Perth, and then there's a number of other ones that we'll show. When do you think the first one went into space? (1960? 1970? 1980, much earlier actually, 1967, and then the second one in 1970, as we'll see in a moment. But we then waited until just after the centenary of Federation, till about 2002 for the next one. So this is the first one. It's RESAT, stands for Weapons Research Establishment Satellite, WRE. It's 1967. It's in space for a goodly time. And it made us, the third nation to launch a satellite into space from our own territory, but only the seventh to actually get a satellite into space. Basically, it was an American Redstone rocket that was at Woomera for various defense-related tasks, and it was spare. And they said, well, we don't want to take it back home. We don't want to just burn it. Can you do something with it? And so the WRE went and put together a satellite, this one that you can see here on the left, in less than a year. And it's about the size of a person. So about,
just a spare rocket lying around.
Yes, with a number of $1 million, yes. But this is one of the things, that often there are spare capabilities there, and it's a question of what somebody can do to do something useful with them. And usually, most of us prefer to help people make something useful. So this is the second one. This is a group of students at the University of Melbourne, so people just a little bit older than you. You can see 3 of them there. And that was built pretty quickly. It's pretty heavy, almost 20 kilos. They waited 3 years to launch. And Oscar 5 here means that it's with the Amateur Radio Association, the International Amateur Radio people. But basically something they were able to put together in their backyard and the physics department and launch eventually. This is the third one, FedSat. This was launched in 2002, so Federation Centenary was 2001, and I came back to Australia in 1998, it turns out. So this one's about 60 centimeters on a side, not too big, not too small, but substantially bigger than my ones, and cost an awful lot more, at least 20 million Australian dollars at that time. So numbers 4 and 5, those are the bottom ones here. Inspire 2, which is the one I led, but with colleagues at the University of New South Wales and the Australian National University. And then we have UNSW ECO, which is this one here, led by University of New South Wales here in Sydney. And this is just a snapshot showing the orbital locations of the 3 of them in space at one particular time in approximately late 2017. But that was the first Australian CubeSat to work in space, and actually the first Australian CubeSat to get into space. And these are 3 of them at ANU. One of the things about building a satellite is it's all very well to build it, but you've got to test it and make sure it works, because it's really frustrating to put all of your time and effort into making something and then putting it into space and it's a brick. It does nothing, doesn't respond. So one thing to do is to put it into a vacuum chamber like this, which is something like 4 meters in diameter, about 10 meters long, pump it down to about 10 to the minus 7 atmospheres of pressure, and then change the temperature. So put it to something which is rather low, like minus 20 degrees Celsius or centigrade, put it up to something like plus 40. Those are the likely extremes of temperature that you're going to come across. And you want to make sure that the antennas that you can just briefly see, this is an antenna here, there's another one here, just wire antennas. You want to make sure that those actually will deploy in space so that you actually get radio signals being detectable. One of the things that you won't know about probably is called cold welding, when 2 metals of the wrong sort are put close together and it's made very cold, they actually weld together. So the atoms will move from one to the other because it's a lower energy state and it's welded, and then it won't ever deploy. And that is super frustrating. So, CubeSats. I've mentioned them a little bit already. Basically, these are satellites made of cubes of 10 centimeters on a side. And you stack them together. If you want to, you can start off with, a 1 unit one, but you can go up to 6U like this, 12U, etc. And they've got a standard, so certain types of electrical connections and systems inside them, certain minimal weights, less than about 1.3 kilos a U. And why do you do it? It's so that you don't have to design your satellite to be entirely bespoke or only your one. Instead, you can, just like with mobile phones, the reason why mobile phones became inexpensive and cheap and powerful is because you had multiple manufacturers building to the same basic standards. So they could say, oh, well, we want a power supply. And you could get it from 10 different places in the world, different capabilities, different prices, put that in, add it to something else, etc. And that's what you can do with CubeSats. It's often a lot cheaper to buy something from someone else than to make it yourself from scratch. Very few of us make our own computers, for instance. I guess some of you might. Are any of you techie enough to make your own computers? Oh, excellent, wonderful. It's not a skill that I've ever had, but I think it's a wonderful thing. And that sort of capability of being able to do electronics, to do the software that goes with it, is really important as you go on. So the basic idea is that then you focus on satellites as a tool. They're no longer something, that people, only the little experts go and work on, toys for the boys and girls, so to speak. Instead, they're tools, things we put into space to do a job for us. And the focus is not the getting into space, but what we do once we get there. And I should have mentioned that the CubeSat standard came from these two people a long time ago, 1999. And we're only now talking about doing an Australian CubeSat standard to replace that globally. So, yeah, basically it allows you to focus on what interests you rather than just making the satellite. Standards and everything can be commercial off the shelf for COTS. And it can be relatively inexpensive. For instance, Inspire 2, my first one, was only about 150,000 Australian dollars in cash. Many people would say that that's the cost of a Boost Juice franchise. So just putting a little store into a mall to sell smoothies. 150K, not very much, but important for you if that's your money. All of the QB50 ones are less than 500K, and my most recent ones are about 1.5 million Australian dollars. And so that means that it's within reach for many of us, in a group perhaps, to be able to put a satellite into space to do something significant. And this sort of amount of money is the sort of amount of money that you can in principle get from funding groups with not too much difficulty. Now, many of you, perhaps the people from China, from the United States, for instance, will look at this and say, trivial amounts of money. And you're absolutely right. Most, for instance, US CubeSats are closer to the 10 million American dollars. This is Australian dollars, so it's a factor of 1.5 as well. But Australia's total space budget is about 0.01% per capita of NASA. 0.01% per capita. So many reasons for being in space. I won't talk about them in great detail, but the most important one for me is public good things. Being able to take data, for instance, of natural hazards, flood events, for instance, be able to save people's lives, to be able to preempt issues. But there's also GPS. I don't know whether your bus driver or your people use GPS to get you here today. I know that I use it routinely, and I suspect most of us do in our day-to-day lives. And that, of course, is all from space. The space weather as well, which I'll talk about more tomorrow. There's an event that occurred in 1859, before even I was born. And that was sufficiently big that it led to fires starting due to electrical breakdown of electric fields induced on telegraph wires. And so all through remote areas of Australia, actually remote areas of the US and other places, you've got little fires, and sometimes big ones, due to the electric fields induced and little, in some sense, lightning flashes that caused fires. And today, if that occurred, it's predicted it would have taken down the American East Coast power grid. It probably wouldn't have been put back up for 2 or 3 years. cost, and just the electricity not sold, is about $1 trillion a year, which is about the cost of an Iraq war per year. So a huge amount of money. And we missed one 10 years ago by 1 week, because if you are the sun and I'm the earth, it went off in this direction here. 1 week takes us a month. 1 week. Okay, so here's another reason. This is too much detail for you to read, but the big point is that launch services in 2016 was worth about $5.5 billion. You know, pocket change, right? Total economy focused on space was about $350 billion. And almost all of this, everything here, is commercial. So almost 80% is commercial. And science, which many of us care about the most, is at most, you know, this bit here, plus some from China, Europe, Russia, etc. Why do governments care? It's because that space economy is growing at somewhere between 5% and 7% per annum, and it's one of the wonderful places to invest your money. There aren't too many industries that grow at that rate long term. And so that's one major reason. The other big reason is everything we do depends upon space today. GPS, communications. Some of you will get TV from our favorite Elon Musk as well. All of these things are only going to increase with time. But let's talk about satellites that are mine rather than big reasons for being interested in space. So this is my first one, little I-Inspire. It was a CubeSat, basically a kit that we could buy from an American group, Xiaofeng Wu and myself and others. We put various little instruments into it. We had it all ready, we thought. And then, of course, this was an American startup that we had bought the CubeSat from. They went into financial difficulties. It never got launched, despite us putting, you know, a lot of effort, a couple of years worth of effort into the materials here. But one thing it did have was a Geiger counter or radiation counter, which we'll see again. But really, we wanted to take perhaps the first images of Australia from an Australian satellite, for instance. Yeah, brownie points, PR, etc. And we had other science we wanted to do as well. But we did launch it to 30 kilometers on a balloon. Have any of you seen one of these big balloons that go up to about 30 kilometers? Oh, neat. Yes, well, these are some pictures of it going up. We went to a group near Adelaide called Project Horus from them, and you can see various of us here, with this being the esky, essentially, with the satellite inside it, and it's me just holding it up as it goes up, and here's just trying to prep it beforehand. So it went up to 30 kilometers, came back down safely, and we had neat pictures of it rolling around in a wheat field, for instance, and various other things. But it's never gone to space. And our next effort, and here's Xiaofeng, by the way, Xiaofeng Wu, Christine Charles, Andrew Dempster, one of my longtime collaborators, Jiro Funamoto, etc. A real combination of people across 3 universities, and that's just a 2-unit satellite, so smaller than this guy. So it's about there, or put another way, it's this top bit here. Really very small, but packed full of equipment. Lots of payloads, too many details here. It's not really important what they are, except that we had, 3 or so. We did much of the work here, and the radiation counter is probably the most important part for this talk. But there's also a GPS instrument from Andrew at UNSW. And it's not just the putting it up there. You've actually got to get the data back down via radio waves that are picked up at your ground station, and that you then do things with. So it's really quite a complicated thing. So this is one, Inspire 2, that did get to space. And let's just do that directly. This sort of talk is not complete without at least one launch. This is the VIP area, about 4 kilometers. Time I see it actually clear the launch pad. But that doesn't stop there. Once you actually get into space, this is a view from the International Space Station. So looking down, this particular one, Inspire 2, went up to the space station with an American company called NanoRacks, then put onto these racks on the outside of the space station, and then basically, when commanded, the door opens and a spring goes ping, just like in Monty Python. And it just pushes out, and it goes out at about a meter per second. So really pretty slowly, in comparison with your orbital speed, which is about 8 kilometers a second. And so I'll just show a bit of this.
Time 10:50 p.m. The ISS just crossed into the Tasman Sea, which is not too far from the University of Sydney in Australia, which is one of our QB50 team members are at. For I-Inspire 2, we are also deploying today Polyiton-2.SAU, the National Technical University of Ukraine, and SNUSat-1 from Seoul National University of South Korea.
Sorry, I'm going to go forward because we don't want to listen to that for all of this time.
Currently working no issues and looking forward to a good deploy. NanoRacks Houston, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and mark.
What you'll see is the CubeSats coming out like this. There's actually 3
NanoRacks Houston, we have good deploy.
together. You can see them starting to separate.
Copy that, NanoRacks Houston. Confirm good deploy. Congratulations to all the teams on the line. Happy to put 3 more QB57.
When you deploy something like that, you know, it's not just going in a straight line. It's often got a little bit of spin, just because the spring might have pushed slightly off axis, or your weight distribution is not right, so you have moments of inertia about a common rotation point. So you actually end up with a spinning spacecraft, and then you have to work at de-spinning it with time. So here's actually the first file downloaded from Inspire, and too many things perhaps, but this is the battery voltage. And battery voltage, and you can see it's pretty stable, but you see a nice pattern, a variation here. Charging current as well. Sorry. And let's just ignore the next one. You can see the temperature down at the bottom varying with time. And so you'll be able to look at this and read off for me, for instance, the orbital period. Right? Because, or at least you would if it stayed in the right place, because we expect when it's in the sun to be getting hotter.
Give you a better laser pointer. Mine was over here somewhere.
But here you see the temperature going up. So that's what you'd expect if you were in sunlight here. And then you're going into a darkness here. And that's consistent with the charging current from the solar cells going to 0.
I can't give you a better laser pointer.
That is okay. We can live with it. And so you're looking at a orbital period, which is something like, well, it's just time difference between here and here. It's about 95 minutes. You can look at the temperatures. You know, and most of us would be really happy with a day like this. You know, it's going between, depending on where you are in the satellite, it's going between about 10 degrees and maybe 24. So a perfect balmy day in Sydney. I'm not sure we'll get to be so warm today for us. But it doesn't have to be awfully cold or awfully hot in space Depends whether your spacecraft is spinning or not. Now this is interesting because we're looking at space weather here. This is time, and you can see a long period of time, approximately 4 months between here and here. On this plot, you see the flux of protons, so the number per unit time of protons hitting a detector. Turns out that these were the first big solar events for about 1.5 years. We launched basically during solar minimum. This is the first event, basically, and you can see it happened, there were a number of them. Here's geomagnetic activities. This is variations in the magnetic field observed on the surface of the Earth. And this is due to energetic particles coming down into the auroral zone and the atmosphere, causing ionization and driving currents and magnetic field change. You see lots of those. But notice here, this is the current from the solar cells and the variations day-night here. And then there's a gap. Basically, our satellite went dead right in here, just towards the tail end of this smaller radiation event. And it was like that for 1.5 months. Every so often we would ping it and try and restart it, and it came alive again. As you can see here, actually it turns out to be another year basically of data that we got. But you might notice that the temperature of the communications device, the radio, was varying nicely up here, and now it's always at 0. Turned out that it remained at 0 forever afterwards because our communications board got fried. And so we no longer had radio contact on command with the satellite, but it was sending out these beacons, just like Sputnik did. Every 30 seconds, it would send out a beacon, wherever it was around the world, and the international radio amateurs would pick that up, put the data onto a site, and we could pick it up. And so the only reason we have data here is because of the international radio amateurs. So I do have a soft spot for them. But we never got the data that we wanted from it. Because just here, we just decided we knew what our spacecraft was doing. We were just going to turn on our instruments and start science. So as they say, carpe diem and be resilient. Do what you can when you can. So here's CUAVA 1. So that's the CubeSat that's on your left over there. And I'm not going to go through it in detail. In fact, that's as much as I'm going to say about it, because it on orbit was dead. Never said a thing. Tomorrow I'll show you some things you can do with a dead satellite, but for now I'm going to pass over it with sorrow. So not everything goes right. Be resilient. So CUAVA 2 and Waratah Seed. So this is a mock-up here, the actual engineering model of Waratah Seed. So this is an industry rideshare satellite where we had competition and 6 startups applied to be on board, with the intention being that they would pay less money to be on board and get space heritage. 5 of them flew, and we also got 2 other experiments from other groups that paid. And then we, as director, I snuck my University of Sydney payloads on as well. But this is, in fact, an engineering model of the thermal management payload from the University of Technology, Sydney, so just down the road. Basically, it's a way of trying to transfer heat effectively from a semiconductor chip, like a processor that might be doing calculations of something. Hopefully not ChatGPT, but you never know. And you want to get that heat away from there, because otherwise it doesn't work very well, and it eventually will destroy itself. And so you can do it in several ways. One of them is just putting a big copper wire on top of it, just conducting heat that way. That works, but a lot of mass. Another way you can do it is the way they did it, which is cleverly arranged tubes that have wax in them. And why do you think wax might be useful? Because it will melt. And it takes a certain amount of heat energy to melt it. So if the heat is transferring up into the wax melting, you can store that heat there, keep it away from the processor, and actually keep it warmer for longer. So it's really quite a simple but clever idea. I better keep going. But you can see I'm wearing CUAVA 2's logo. If you want to learn more about Waratah Seed, there's a website here, for instance, all sorts of details, but I just don't have time. Happy to talk about it, but I don't have more time, except really here's an image of some of the Waratah Seed team. Not sure whether you'll see Anita Howe-Bailey here as one of the lecturers.
Not this time.
Not this time. Anne Battens, all sorts of other wonderful people. Shirley-Ann Bai, who's my chief engineer, and Patrick Opel, for instance, and others who are great. But I wanted to talk about CUAVA 2, and we're going to listen to a video about that, please. So as you can tell, some PR, but I thought it's an effective way of maybe showing some things. But you have to test, as I said, your experiment, make sure it works properly. One of the and this is the actual Waratah seed in its protective case. The protective case is here, but that's a mock-up, as I said. And then here, so that's ready to be transported. Here, one of the hardest things I've ever done is to take my satellite, put it into a case that allegedly is protective, and what you see, put it onto a so-called shake table. So this is a huge, probably, it goes back about 3 meters, and it can push a 1-ton object back and forth at something like up to about 1 kilohertz. So the acceleration as it goes forward and then back and then shifts is at least 10 times g, so 10 times the acceleration due to gravity. So we're testing to see whether our satellite will hold together under the launch vibrations as it goes up into orbit. And you test it beforehand. And when you walk into the place carrying your, in this case it was CUAVA 1 Inspire 2 when I first did it, your little CubeSat, you'd spend all this time and effort with your colleagues in doing it. And you're going to a machine that's just practicing, and it sounds like a freight train. And you're going, no, I'm not going to put my device on that. It'll destroy it for sure. I ended up doing it, of course, and it worked fine. But it's one of the hardest things I've ever done, to actually trust that we'd built it well enough to be able to do that. I could have shown you a video of that, but I thought it wasn't worth it. Instead, I thought I'd show you some of the TVAC or thermal vacuum. So that's in this great big thermal vacuum system that you saw the 3 little satellites in. And one of these is CUAVA. So let's see, this is CUAVA 2, this is Waratah Seed. Here we are with in infrared, and this is the UTS people testing their thermal management device. And you can see the 2 satellites there look different. In this case, that's because I think this one is actually Waratah Seed with the heating element. But the other thing you probably should do, and this is we did this after CUAVA 1 didn't work, was to take our satellite outside. And so, have any of you been to the electrical engineering building?
I don't think we have this time.
No. So it's about 1 kilometer in that direction, I think, over the bridge and the other side. And this is the top of it, and it's got our radio antennas on the top of it here. And there's a nice student lawn in front, and we took the satellite outside. So here's the satellite, here's our ground station equivalent. What we wanted to do was let it turn on, come alive, send it signals saying, I'm here, I'm alive, do the radio contact back and forth, because this is the best test that it'll actually work in space. If it works here, you can be very confident it'll work in space. And for both of them it did, and here we have some of the radio transmissions here, frequency across here, here's the radio signal that we expected to get. So we were feeling pretty confident when we put it into space, although you can see here Shilian and Patrick at EXO launch in Germany, in Berlin, just giving the satellite over to be integrated. And then it got launched a little bit later, 17th of August last year. And it's now been in space for a while. Maybe I should skip over this. It's just another launch. Okay, this one doesn't have sound, which, but this is actually Vandenberg in the States, in California. So the Secret Squirrel launch site, and it's SpaceX Transporter 11 going up. And eventually, we will see the deploy. So this is always great when you look down and you can see the images that they have from the cameras. It's just wonderful. But I'm going to go to here. Oh, did I go too far? So that was Waratah Seed deploying. Pretty quick, and not a lot of sunlight to be able to see it. But those 2 satellites have now traveled more than 1 astronomical unit around the world. They've gone roughly 2,000 orbits now, almost 1 year in orbit, and we only expect it to be 6 months alive. So we're certainly battling and doing wonders for our clients. And here's just a little bit more. This is the GPS instrument for GPS reflectometry. But what do you do with GPS? One of the things you do is navigate. And so this is the orbit across the world, or around the world. Here's Greenland. This is the prediction of the orbit here, the TLEs, the prediction, and then this is the solution from the GPS that's running. How does it run? It receives signals on its antennas, and it identifies them as being GPS satellites, and a particular GPS satellite whose position is known, and then it just triangulates with it. And the next slide just shows some of the satellites. Instead of calling them GPS 1, 2, 3, 4, etc., it's PRN, etc. And these are just some of the many GPS satellites that it was receiving at that time. So lots of them, and it's continuing to do that. So what about Harry Messel and Sputnik? Here are some data from the radiation detector on CUAVA 2. A student, Rayan Al-Qadri, who's about your age. He's a tiny bit older, might be 19 rather than 18, but a first-year student, has worked with me and Patrick and others. And the situation is basically like this. Here you have the sun, not to scale, of course, the Earth. Here we have magnetic field lines. The purple ones are the standard ones for the Earth. But actually some magnetic field lines, due to a process called magnetic reconnection, which I'll talk about a little bit tomorrow, actually connect from the sun all the way through the so-called magnetopause down towards the Earth. And the aurora that we're all used to seeing in a nice auroral oval, down here in the south as well as the north, that's from a region where the magnetic field lines are open to the solar wind and the sun. And so you're seeing energetic particles coming down right there, precipitating, hitting atoms. When the atoms are hit, they get some extra kinetic energy, and that some of that energy goes to excite electrons from one orbital around the atom to a higher orbital, and then they re-emit the excess radiation, and that's the light we see. So what we're expecting to see is energetic particles around here, over the poles. And so what we have here are counts in a logarithmic scale of here as a function of latitude. So going from the North Pole at plus 90 to the South Pole at minus 90. And you can see here's the standard numbers. You see a little bit of an increase over the auroral zones and poles most of the time. Not much around the equator. So here in Sydney, for instance, we don't have much of an issue with radiation damage, even on airplanes. But sometimes when you go over the auroral zone, you see these big increases. That's due to space weather events. So if you fly towards Antarctica and you go to South America in particular, you go at the wrong time, you can get radiation events. They're quite careful about that. But you notice this event here, that's actually repeatable. And I must admit, I didn't believe that the so-called Southern Atlantic anomaly was going to be significant. Yeah, people had said it. I just didn't believe it. And I was sort of right in a way, in that you can see that the difference between here and here is only about 5 units, which is about a factor of 3. But look, compare with the normal values. Factor of 1,000, if not 10,000 larger counts. So this is the so-called Southern Atlantic anomaly, and when you look at a map of the world here with latitude and longitude, red here corresponds to the orbital path, so each of these is an orbit, comes down here and then it will go up somewhere here, then down another one. We're seeing increased counts over the so-called Southern Atlantic anomaly, which is a weak region in Earth's magnetic field. If you look here, this is an old prediction, observations of the strength of Earth's magnetic field as a function of latitude and longitude. And so just reading your contours, this turns out to be a region of low magnetic field strength here. And over, for instance, here, 60,000 microtesla. sorry, nanotesla, so 60 microtesla. This is a large magnetic field strength here. So it turns out that close to the Earth, you're told, the Earth's magnetic field is a dipole. It's not true when you're close to the Earth. Within about 1-2 Earth radii, big perturbations. And it's only once you get further away that you see a nice dipole. And here, Southern Atlantic anomaly, the magnetic field is weak, and it allows these energetic particles to come down closer to the Earth and be detected by our satellite at 500 kilometers. So this is the full circle here for Harry and radiation, actual observations of radiation energetic particles seen by a University of Sydney experiment, something like, well, how long is it? It's 17 years after Harry Messel obtained the data from Sputnik and wouldn't release it for others to collaborate with. So we've got various projects that we intend to do with this, including looking at how the Southern Atlantic anomaly varies with time, looking at space weather events here, and correlating those with other events. And I won't talk about that. But here are the conclusions. Look, maybe I should just shut up and see if there are any questions, but I guess a very quick summary is that we've got a number of satellites working in space at the moment, driven here at the University of Sydney and, in fact, for Australia. So it's something you can do, whether you're from Australia or from international places. You could come and work with us on that, and we could work with you on it. CubeSats are great because they're powerful, they're inexpensive, they often allow you to concentrate on what you want to do, which is often the actual experiments rather than the building of something. But some people, they want to do the building. That's fine. You can do fundamental science, and it's the science you can do from space, so looking down at the Earth, for instance, or looking outside, or it's what you could just study space itself, the plasma, the space debris, for instance, which my little instrument, Eddie, is meant to look at, for instance. Great area to be in. It underlies all of modern life. Space is vital for everybody. Australia's government doesn't yet fund it really well, but hopefully they will further. And I'd like to talk some more about it with you. So thank you very much for your attention.
Thank you so much, Iver.